Hello, everyone, and thank you all for joining us. Today's webinar is Metal to Plastics Conversions, Design, Materials, and Tools, and is presented by BASF. Your presenter today is Bill McMaster, Application Development Engineer at BASF. Bill has been involved with plastics application and development activities for over 25 years. My name is Carly Sheeter with UL, and I'll be moderating today's webinar. Now I'd like to turn the presentation over to Bill.
Thank you, Carly. Today we're going to talk about the process to convert challenging metal parts over to plastic. Okay, so why convert to plastic? The number one reason is cost reduction. This really is a win-win for both the consumer and also the OEM. The consumer gets the lower price, the OEM gets higher margins. So it really is the number one reason to convert. Weight reduction would be probably the next reason, and it applies for a lot of applications, not all, but when it's important, it really is important. Automotive would be one of the key ones. Automotive is always trying to get more fuel efficient, and the best way to do that is to lower the weight of the car. And plastics do that, and automotive has been doing that for years now. Hand power tools is another great example. If a construction worker is going to use a drill or a chainsaw or a circular saw all day, obviously that's a lot of fatigue on his muscles, and basically a lighter tool is going to help that. Next reason would be improved chemical resistance. Each plastic has different characteristics with regard to chemicals, so they should be looked at before deciding the plastic. But in general, if you choose the right plastic, in this case here, a good example compared to metal and plastic would be steel versus any plastic. Steel is going to rust. If it sees water, you have to paint it, add additional cost, where any plastic is not going to rust. Improved aesthetics. Many metals you have to paint or polish. Plastics in general, especially injection molded parts, you can mold parts, mold it in color, and what you get out of the mold usually is the final part. And lastly, part consolidation. It allows you the freedom to reduce the assembly down to fewer parts, and that can reduce both time and cost and makes a more reliable assembly. So what are some of the benefits of plastics over metal? Greater design flexibility. This is a big one. Again, we talked a little bit about combining parts, so that's nice. Color coding key parts, say a drill housing. You can color code the trigger. You can color code something to really identify this is where you pull the trigger or you start something. Add textures. You can use snap fits versus screws. A lot of advantages to using plastics. Increased tool life. Injection molded tool life basically is longer than a die cast part, and it's up to like 6 times longer. So that's a nice little benefit. Increased strength to weight ratio. In general, plastics are not as strong as metals, but because of the lower weight, we can design it and make it stronger. And we'll see that in some of the slides coming up here. Reduced secondary operations. Typically, say in a metal stamp part, you stamp the part, you get a part pretty quickly, but unfortunately it creates a sharp corner and a burr, and the process, the part actually has to be deburred. It's an additional operation. If the process isn't done right, then the consumer can actually cut themselves. You may have to polish the part. In general, in plastic parts, there's no additional operations there, so a nice benefit. And the last one would be warm to the touch. Reduced thermal conductivity really accounts for this. And the best example of this would be for the older audience here that can remember when door handles on cars were actually die-cast metal. Basically, you had to take off, when you didn't have a glove on and you opened your door, your actually skin would stick to the metal on a really cold day. That no longer happens with plastic. So we chose 4 properties here. There's plenty of properties we could choose here, but these are somewhat 4 key ones. First one in the left top corner would be specific gravity. And basically that's just really the weight or the mass difference of the materials. What we're showing here is unfilled nylon, so really an unfilled plastic. We chose nylon, but it really could be any unfilled plastic. And a glass-filled nylon, which is really a reinforced plastic, and then aluminum and steel. So from this comparison, you can see that the weight comparison of even the filled plastic is half of aluminum and probably 3 or 4 times less than the steel. So a nice reduction. Next one will be thermal expansion. And this will apply when you have an assembly with a metal part and a plastic part. They're going to grow at different rates, and that can be key in your design. So what this is showing is an unfilled plastic is going to grow significantly, and you should take that into account. But if you have a filled plastic, you can reduce that, and you're much closer. So again, something to keep in mind when you're designing your parts. Strength. This is showing that unfilled plastic is significantly less than the metals, but the filled plastic is close. It's close to aluminum, and it's not that far off from steel. You can really design around that fairly easily, as we'll see. And then the last one is stiffness. This one's a little more challenging. As you can see, the unfilled plastic nylon in this case, and the glass-filled, the reinforced plastic, is significantly less than the steel and even less than the aluminum. Knowing that, it's a challenge, but that never stopped us. We can get around that, and we'll see how we do that later in the presentation. So in your material selection, the first thing you're going to get is a data sheet. And at first glance, you see a lot of good information. You see stiffness information modulus, you see strength data, you see strain data, you see impact data, a lot of good information. But with that said, you should only use a data sheet for screening purposes, and it's rarely used in design. And we'll explain why in the upcoming slides. So you have your application that you're thinking about designing in plastic. So first thing to do is what I like to do is to pick 3 most important requirements of your application. So is it impact? Is it thermal? It's going to see high temperatures. Is it fatigue? Whichever, and again, I pick 3. In some applications, it's more, but the top 3 are probably the most important. And in some cases, it's only 1 or 2. But I guess the point is to know what is important for your particular application. And the other thing to keep in mind is, where is this application going to be? What environment? So is it going to be in cold temperature? Is it going to be, for those people in the States, is it going to be in Alaska in the winter at -40? Or is it going to be in Arizona in the summer, where it's going to see both UV and high temperatures, or even both? So if it's both, then you need to keep in mind, worst case conditions for both temperatures. Okay, so you've gone through a little bit of the screening process. Now, this really helps to have a little experience to know some of the basics of the material. And if you're just getting started with plastics, you probably won't know, but you can lean on your resin supplier, such as BASF, to guide you with this. So basically, knowing the strengths of some of these plastics is key in your selection. So in nylon, it has high strength, some high stiffness, but its real key is excellent toughness. It's hard to break. So if you're going to have an application like that, pick a nylon. Polyester, excellent dimensional stability. Acetal, good frictional properties, good wear properties for gears and chains and things like that. Lastly, a polysulfone would be a high temperature material where you're going to see those super high temperatures and you need good chemical resistance. Really, what is design? So we looked in the dictionary for this, and it's to create, execute, or construct a plan that improves parts or details. Basically, it's to make something better. And if you're designing a new part or assembly, that's really what you're trying to do. You're trying to make something better. So keeping that in mind, going through all the steps is important. So we'll go through these steps here. So basically, you want to define, what do you want this part to do? Once you know that, now you can sketch maybe a concept and what you think the part can look like. Then you can define, okay, what are your requirements? What are your loads? You know, maybe those top three that I talked about earlier. Then from there, you can estimate some stresses, especially if it's a structural part. And you do this by hand calculations. Even if it's a complex part, it's a starting point. Then from there, now you're ready to select the material or start investigating material options. Really not selecting the material yet. Then you determine your wall thickness, kind of a starting point. And now, especially if it's a complex part, we're going to use CAE. We're going to use probably a finite element analysis to do a stress analysis. So that'll give you a feel for, is some of these materials, which ones at this wall thickness are going to meet these loads. And if they're not, you're going to have to up your wall thickness. Then you'll conduct a mold filling analysis to determine where you're going to gate it. And then you can optimize these results using CAE results, as we'll see here in the upcoming slides. And lastly, once you simulate all this and you're comfortable with your design on the computer, now we're ready to build a tool. So once you build your tool, you get prototype parts, you test them. Hopefully everything looks good. But if not, if you've done your homework, you probably have to revise the design one or two little tweaks, and you should have a successful part. So to get that successful application, it's really what I call a bullseye. So basically, design is very important, no doubt. But basically, you want to choose the right material, and you also want to choose the right process and do the right processing during that process. So that would be, this is the bullseye right there. And in it all is basically knowing your environment here, as we talked earlier. You know, what are your worst case conditions? Temperature, humidity, UV. So let's look at that data sheet. Earlier I said you can't use this for design, and now I'll explain why. So basically, you look at this data sheet and you see some good properties here. The modulus is 10,000 megapascals. The strength is 170. You say, wow, it's good, strong material. Well, but then you say, okay, in my application, I'm going to see humidity. This particular material will drop with humidity, so it's dropping 30%. And this application is going to be 80 degrees C. Well, we're going to lose another 25%. And this application is going to be CUV, extended periods, well, that's another 10% drop. And lastly, it's going to see some high temperatures for long periods of time. Well, that's another 10% drop. Now, these numbers don't look as good. We're at 2,500 megapascals, and the strength now is 42.5. So really, this is what you want to design to. You want this material to withstand this kind of stress. You want to design under this. If it was strength, you want to design under 40 megapascals. So stress strain curves. We've all seen metal ones, metal curve, and nice curve where you got a nice yield. You just design below this yield point. So with plastics, structural plastic is somewhat similar. Basically, instead of a yield now, you're basically getting a yield and a break pretty much at the same point. So you can design in this area here. A ductile plastic, you want to design in the beginning here, and you don't want to design way out here where the material is yielding. So well, let's look at stress strain curves. To add something else to it, we're going to add temperature, where we don't have to worry about that in metals. In plastics, we do. So if you ask for a stress strain curve, you may just get 23 degrees room temperature, and that would be right here. And again, you could design to that. That's saying 200 megapascals. That's a pretty strong material. That's nice. Well, but if your application is going to see 100 degrees C, then you're going to be way down here, and you may be at 100. So you're going to be half at that. So understanding that is key. So basically with temperature, you really want to balance strength and elongation. As you can see, strength is going down with temperature, and elongation or strain is actually going up. So worst case, if you have both extremes, your part is going to see minus 20, say it's going to be in that Alaska, and then you're going to see 80 degrees C, you're going to be down south in the sun, then basically your worst case conditions will be for elongation is going to be this number. It's only 2.2, whereas for strength, it's going to be the high temperature at 130. So let's look at some basic rules of thumb, some plastic 101 tips, as I call them. So uniform wall thickness. This really is key for any plastic, and I'll explain why. If we look over here at the green part, if this was your first design, you may design it like this. Well, this is a very thick area, and this is a thinner area, and this, because this area is going to cool longer than this area, it can put in some differential shrinkage. It can give you some warpage. So it's just not a good design. Basically, if you can get more of a uniform wall, like this part has been redesigned, now this wall and this wall are about the same, and this, and I'd even design it a little bit further. I would put a little bit of a divot in here to make it all uniform. And this will give you a low stress material and minimal warpage. So let's go to stress concentration. Another important attribute for plastic, and it's actually, it doesn't only apply for plastic. Stress concentration is for metals and plastic equally, but for plastics, most of the time we're designing with a smaller factor of safety. So in that case, stress concentration is usually more important because of that. So this is a typical stress concentration curve. It's a cantilever type load where you have a bending load, and then you've got a cantilever beam here. And what it's showing in this curve is your stress is going to go up if you have a sharp corner right in this area here. This is bending, and it's going to break no matter what here. But now that you have this sharp corner, small radius, you're going to be in this vertical range. Ideally, if you can design it where you're in this horizontal range, then your stress concentration is small, and that's really what you want to do. So looking at an actual part. So this part here, not exactly the same as the handbook stress concentration, but it's basically very similar. So we can use that curve. So now we have a load, we have a cantilever here, we've got a radius here. So okay, before we think about stress concentration, the normal way to do it is, okay, this is just a bending. Everybody knows the bending stress is MC over I. So that's a quick calculation. You run through the numbers and you come up with a stress of 9,600 PSI. Well, say the plastic you picked was 15,000 PSI. You'd say, okay, that's good. I got a 50% margin of factor of safety in there, so it's going to pass, no problem. Well, if you built your tool, it would fail horribly, and you'd say, why did it fail? Then you would go back and you'd say, you know, it broke right here at this sharp corner. Well, let's go through and let's go find that stress concentration curve. You do all that, and now basically your R over T, which is here. So R is 50 thousandths, T in this case is 0.25. You come up with a ratio of 0.2. You're over here. You come up here, and now it's saying your stress concentration is 2.5, which is huge. And basically it's saying, okay, the real stress in that area, because of this, I'll call it sharp corner, is 24,000, and that's why it failed. Easy fix is now just to increase this radius here, and if you can get it down in this area, you'll make a big improvement. You can lower this by a factor of 2 easily. Okay, so let's talk about fillers for plastics. This is how we get additional strength and stiffness, and glass is one of the common ones, but there's other things too. Glass has a high aspect ratio. Basically, its length is much longer than its diameter. So what that is, I like to describe it as logs in a river. You're going to gate it, you're going to inject plastic here, and now the glass, which I'll call logs, are going to line themselves up in this direction, as we're showing here. Well, what that does is if you pull this part in this direction, pure tension, this way and that way, it's going to be very strong. That glass is going to help you. But if you pull it this way, it's going to be much weaker. That glass really isn't helping you. So understanding that is key in a lot of applications, and we'll show exactly why. The other point here is the material, when it comes around the hole or obstruction, is going to create what we call the weld line. You see it right here, and basically this is a weak point. It comes around here, it's a little bit cooler now, it melds together, but it's a weak point. So understanding that, if this is going to be a high stress area, it's probably going to break before you want it to. Okay, just quick time check. It looks like we're somewhat on time there, so we'll continue at this pace then. So equivalent stiffness. One of the earlier slides we talked about stiffness was a challenge if you're converting a metal part to plastic, and it can be. But if you attack it right up front, it's doable if you have the space in your application. So here's an example. You have a steel part. Say this is your cross section of your steel, and basically you want it to be just as stiff as the steel. So there's two things in stiffness. One, everybody knows the material has a stiffness, and that's your modulus, if you will, and that's on our data sheet, and again for room temperature. But the other stiffness is a geometry stiffness, and if it's bending, it's the moment of inertia. For a rectangular section, it's going to be I equals B, this base, compared to your height, which is cubed, divided by 12. So really, if you want to increase I, since H is cubed, that's the dimension you want to change, and that's what we did for the aluminum. example here. So for aluminum, its modulus is 3 times less than steel, but we don't have to make it 3 times higher. We make it a small amount higher, and we get the same exact stiffness. The R value rigidity, we'll call it EI, is the same exact value. So now we want to do it for plastics. Well, first of all, we want a uniform wall, and we don't want too thick a section. It can create voids and other issues. So we're going to core ours out. But this height is our key. So that's what we've increased here, and we have somewhat of a uniform wall here. Our modulus, you can see, is a factor of 30 almost, smaller than steel, yet this geometry is much stiffer, and basically now we've achieved the exact same rigidity of this part, and if you look at the cross-sectional area, we're actually less than the steel, and that coupled with the reduced mass will be much lighter than the steel part. So this is going to help us with strength and stiffness for a structural part. So there's many types of ribs out there, but we're going to talk really about 2 of the basic ones, and it would be straight ribs, which are good for bending, and then cross ribs, which are good in general for torsion. So this is a handy curve for your files when you print out the presentation. So again, this here we talked about is great for bending. If this is going to see pure bending, you don't need to have, this is showing this angle right here. So it would be a 0-degree angle, and it would be this. If you're going to be in pure torsion, the part's only going to see torsion, then basically the best case is probably 55-ish, you know, in this area, between 50 and 55, or 50 and 60, that would be that angle. But most parts, if you're going to see torsion, you're going to see bending as well. So ideally, most parts, you're going to shoot for an angle of 25 to 30 degrees. So getting back to ribs, and again, this is another good one for your files. We'll go over just some basic rules of thumb. So first of all, your ribs should be thinner than your main wall thickness, usually 50 to 80% of the wall. Next, you want to have a rib that is somewhat high. You don't want a real short rib. It's not going to help you much. So you want to be at 2 to 3 times the wall thickness here. And you want to space them a certain distance. And this is showing a 2T. You got to, you know, if it's too close, it's going to create other problems. And then lastly, you want to have a draft on here so that when you pull this out of the mold, it doesn't get hung up. And obviously there is your radius in there, that's stress concentration. So the bigger you can go there, the better. So structural ribs add structure, which is great, but they create another problem if you have an aesthetic part. If you don't have an aesthetic part, it's not a problem. But if you're going to be, this is a show surface, what this rib, in this case here, we're showing a 1-to-1 rib to wall. So you could make this thinner. That's one way to get rid of it. But you're going to get, we'll call it a sink mark. So it's a depression here, and basically it's caused by shrinkage. This here is a bigger section than over here. So it actually, and you can notice if you pick up a plastic part, you'll see this on a lot of parts. But if you put a texture on here, you can minimize or not see that, which is nice. The other thing you can do is just put what I call a change of feature in here. You're just changing the contour. You're putting it right where that sink mark would be, and your eye can't pick it up. It's such a small depression. The change of feature works well. So for a structural rib, how big should you go? And that's a question. It really depends on your application, but let's go through a short example here. So basically you're brand new to plastics and you're designing your first part. You design it, okay, this is what you design. This is a flat rectangular cross section, and you bring this over to your boss and he says, it's just flimsy. It's just not stiff enough. I need something much stiffer. So you go back to your desk and say, I can make this stiffer, not a problem. So you double the wall thickness, and now you look at it, okay, and the stiffness went up a factor of 8, 700%. It's like, this is pretty good. And you're about to go back to the boss and tell him that, and then you think about it, it's like, I doubled the weight and I doubled the cost of the part. That's probably not a good thing. Well, I went to that BASF course, and they say, I can add structural ribs. Let's do that. So let's jump right to number 5. This is that 3-to-1 ratio we talked about. So now you put that rib on there, and now the stiffness goes up 925%, so over a factor of 10. Huge, nice. And now with that rib, the weight and part cost went up roughly 19%. So you're much better. This one you could bring to the boss. In reality, maybe, depending on your application, you might go in between these two, or you may even go down a little bit, because even this one's 4 times as stiff as your original one. So this is a handy chart, even before you get to the ribs. So basically, if you're looking at your cross section, and I use this chart, I go back to it from time to time in the very initial stage concept when you're trying to come up with a part design. So if your application is only going to see bending, flexural, then what's this saying? This is saying, okay, these are all equal cross-sectional areas. They're not shown that way, but the cross-sectional area is the same. So they would all weigh the same. So basically it's saying, okay, the most efficient design for bending is a I-beam, a narrow profile. And you think about it, that's why buildings and bridges and everything are using I-beams, because it's the most efficient. And then it goes down a little bit. There's a U profile, or I'll call it a C profile, a wider I-beam, and then interesting enough, some hollow sections look pretty good. So knowing that, okay, good. But if your application is only going to see torsion, what do the cross sections look like? Well, it's saying the hollow sections work the best. So in a lot of parts, you're going to see both torsion and bending. So which one do you pick? And from this chart, it really helps. It's saying, okay, ideally, if you can pick the hollow sections, that is pretty good. You get pretty good bending and you get excellent torsion. The only issue is, can you mold this hollow section? Maybe if it's an extrusion, it's easy. If it's an injection mold, you may not be able to pull it too far, and maybe you can do gas assist. So you may have some options, but if you can't, there's another thing not on this chart, but basically we can use some cross ribs, especially in this U profile, this X cross ribs that I talked about earlier, and basically that can help your torsion. And now this thing would go much higher, and you have great bending and torsional stiffness. So let's go to an actual part. In fact, this was a part I worked on many, many years ago, and basically it was a bracket, cruise control bracket, and it replaced the metal part. And the engineer came to BASF and said, okay, we designed the material out of your material without your knowledge, and basically it's not working. It's bending too much. Can you suggest another material? So we looked at it and said, okay, well, why is it failing? So is it the material, like the customer was indicating, the engineer was indicating? Was it processing? Maybe they processed it wrong, or was it a design issue? So it's usually one of those three. So, okay, before we do too much, okay, they talked about this was a stiffness issue. Okay, well, let's go back to our R equals EI. So, okay, well, we understand this concept. Okay, so if you have this rectangular cross section, basically we know the moment of inertia, I, is equal to BH cubed. Again, the height, if you will, is cubed divided by 12. So we know, okay, well, we can attack the design if need be. And if we double this, again, we know it goes up by a factor of 8. So before we do anything, let's try to look at the original steel part. Let's do an EI on it. What's its rigidity? So we went back, we got the steel part, we measured thicknesses, and we did everything here. There was no ribs in the middle because it was a stamped part, but it worked well. So, okay, its EI was 6,000. Okay, that's a nice number. Well, let's look at the present part that they were complaining about. Well, its EI is only 592. Oh, that's a factor of 10 different. No wonder they're complaining that it's just not stiff enough. So, okay, how do we, do we have, we can look at a different material, but to go up a factor of 10 is going to be challenging. So let's change the design. So here, we're going to change this design. We're going to make this height taller, and we're going to make these ribs even a little taller. And you can see here relatively what we did here. And now we get an EI of 30,000. We're actually 5 times stiffer than the steel part. So anyway, the OEM took our advice, changed the mold, and everything worked great. In fact, it actually performed better than the metal part. So again, if you gate your part, here. You're going to inject the plastic here. This is what we call a fan gate. So the plastic injects down here, it comes here, and now when it launches in your part, all the glass is lining up, lodged in a river again, right down here. So this magenta part is going to have some really good lining up in this direction. The blue part, it's going to line up this direction. So it's really we'll call it cross flow for this geometry. So the magenta part, and if you just look at tension, is if you do a stress strain curve, it's going to have 110 megapascal strength. It's going to be fairly strong. Now we look at the blue part, molded basically out of the same plaque or the following plaque. You molded 2 plaques, you cut this one out of the first one, you cut this one out of second, and now this one here is only 70. So a huge difference. So in a complex part, you're going to have many different directions. We could cut a 45-degree here, and it's going to be in between these. So understanding that is key if you're going to design to a small factor of safety. So how do we do that in a complex part? In the plaque, it's kind of easy, but this complex part, now you can see here, the material is flowing all down here, and you're getting some good flow this way, but you're getting cross flow over here. And if this is a high stress area and this is a high stress area, how do you calculate that? Well, we do it with a computer. We developed a software called UltraSim that from our mold filling analysis, we know the glass orientation, which is great. In our FEA, we calculate stresses, which are good, and they're accurate, but unfortunately, the strength was not in there. So we use UltraSim, so at any given point, its strength may be weaker because it's cross flow, and it may be stronger where it's inflow, and our software takes that into account. And therefore, we can accurately predict if a part is going to fail in any area of the part. So this is showing it in a little closer detail on another part. So basically, if you gate here, you inject your plastic here. Well, when you inject it there, right at the gate, you're getting somewhat random orientation. So it's green. This here, this orange area, you're getting highly oriented this way. It's kind of strong in this direction. So knowing that, uh, our software takes that into account. So in this area here, the strength is going to be 205 megapascals, whereas in the green, it's only going to be a little bit less than 100, maybe 98. So basically now, in our FEA, in our structural analysis, we predict all that, and we actually predicted and do it many times on complicated parts where this part is going to break and accurately what load it'll break at. So long-term properties, fatigue is one of them, and many applications don't involve fatigue, so you don't have to worry about it. But if your application does, it's a very important property to look at. Otherwise, your part will fail much earlier than you expect it to. A good example of fatigue would be a fan blade. A fan blade is spinning at high speeds, and basically the stress on the blade is going to go back and forth between tensile and tension, and tensile and compression, and basically will fail much earlier than what the data sheet ultimate strength is saying it would. So basically, we're showing two different temperatures here. So let's concentrate on 23. So say that fan, you were going to target 1 million cycles. You probably want to go further, but let's just go to 1 million cycles. So if that was the case, and your application, this fan is only going to be seeing room temperature, then where do you design? Anywhere under this line here would be fine. So without any factor, you would design it for 60 megapascals. So that should work, and it's not going to fail until you're well more than 10 million cycles. So that looks like a nice factor of safety. But now you could come up with a new application with that same fan. They say, okay, we want you to use this fan, but it's going to be in a high temperature atmosphere. It's going to see 100 degrees C for long periods of time. It's like, oh, that changes it. This fan is not going to work. It'll fail miserably. In fact, it'll fail in minutes, really. So if you would have to design a new fan or make this fan blade a little bit fatter, the blade thickness-wise, now what you should target here is probably around 30 megapascals in this area here. So huge difference. So understanding, again, as we talked about temperature, your temperature extremes is key in any property, including fatigue. So creep. Plastics will creep. Other materials will creep too. Actually, metal will at super high temperatures, but in general, most applications aren't seeing those high temperatures. So in general, we think of metals not creeping, but wood will creep. So a good example of creep for those people that aren't familiar with it is, say you have a bookshelf and you put lots of heavy books on it, and basically it was a cheaply made bookshelf. Basically, over time, the wood shelf will actually bend, and it'll deform, and it'll actually, or sag, I guess is a good word, and you'll see that, and it'll be noticeable. So plastic will do the same thing, and in plastic, it's not only stress related, like that wooden bookshelf with lots of weight, it's a high stress, it's temperature related as well. So we're going to show some creep curves here. And basically, this is a creep curve. Ideally, you want something with a very level slope, something with a more of a vertical slope is not a good thing. So if you design your first part and you use polypropylene, and basically it was in a creep application, and you design the cross section and you say, okay, the stress was 5,000 psi. Okay, you know, your ultimate is much higher than that, and you didn't really look at creep. Well, your thing would your application, say it was you're placing that metal shelf with plastic, it's going to fail within minutes. It's going to be real quick a failure. Well, let's change the design. Let's make it 3,000. We're going to make that shelf a little bit thicker. Boom. Well, it still fails. Well, now we're going to make it really thick, and we're going to make it down to 1,000. Well, it's better. It survived 1,000 hours, but it's only a matter of time where it's going to fail out here. So the better choice is to go to a high temperature material that can withstand that temperature too. In this case, a nylon. If you had 5,000 in your original design, again, you have that little bit of slope. It's probably going to last well above 1,000, maybe 10,000, maybe even 100,000. That might be acceptable, but a better design is probably going to 3,000, and here it's probably going to last a lifetime. And then if you're really conservative, you can go down to 1,000, but this will last 2 lifetimes. Okay, our last example here. So gating. So now you've designed your part and you're satisfied with design, everything looks good, and now you're about to build the tool. Well, the last thing you want to do is just throw it over the wall to somebody to build a tool for you. You really want to stay involved, and this is a good example of why. So here's your part. You can gate it in a few different scenarios, but we're showing 3 here. You can end gate it right here. You can gate it with 2 gates and get a knit line here, or you can just gate it with 1. Well, if you throw it over the wall and don't give any input to your tool maker, he's probably going to choose this one because this is the easiest way to build the tool. You just come right down here, and it's the most cost-effective way to do it. But saving money on the tool and getting a failed part is not a good way to go. So this is showing, okay, say your load case here was an impact right in the center of the part. This gating scenario passes. This one here fails miserably, breaks at the knit line. And then if you gate it in here like the tool maker wanted to, this one fails too. Not quite as quickly as that, but it still fails. So the best case, with this requirement, is case A. Just a quick review: why convert to plastics? Again, cost and weight reductions are the big ones. Part consolidation really helps assembly and reliability and improve aesthetics. So how are you going to do it? Using good plastic design principles, identifying and designing for worst case conditions, properties, whether that's temperature, humidity, whatever those worst case conditions are. And lastly, especially for complex parts, using CAE to your advantage really helps you confirm a design and simulate that before building your tool.
Thank you. And thank you to everyone for attending today's webinar. Have a great day.
BASF. We create chemistry.